Hello, this video is inverse trig functions differentiation. So we're going to take something you've probably seen before in a trig or pre-cal, inverse trig functions, and apply calculus ideas to them, just like we've had the derivative of the regular trig functions. So I'm just going to give you kind of a brief synopsis of what's going on here. The idea of inverse functions. Now some books make comment like, well, actually, technically, trig functions don't have inverses. And that's true, so it almost sounds like, well, then we can just quit and call it a day here or whatever. But that's not what's going on. They don't, technically, because one of the properties of a function to have an inverse is, regular functions, everybody's pretty much probably familiar with the vertical line test, but it also has to pass the horizontal line test to be what's called a one-to-one function and therefore have an inverse. So all the trig functions, if you look at across all real numbers, they would all violate that property because they all kind of cut through. There's some of them that, well, sine and cosine are obvious, but secants or cosecants do these kind of things here. And tangent kind of goes like this repeatedly over and over, kind of does this, and then because it has asymptotes in there, so does the secant, like that. Well, anyway, so it was decided to let's pick a range of values, and then if you pick a certain range of values, then you can allow it to have an inverse. It's sort of like if you took a parabola like y equals x squared and just said, okay, we're going to define this with x being greater than or equal to 0, where you only have the right half of it like that. Well then, yeah, that would be okay if you did that because it would satisfy the one-to-one property. But a regular parabola, the entire thing would not fail the horizontal line test. So y equals sine x, basically inverse functions, you're essentially reversing the x and the y. Log and exponential function work that way. And arcsine is just that's arc. We just call it arcsine. That just means arc means inverse, but obviously you're free to use this notation, sine raised to the -1. Which I like this arc. I'm glad somebody came up with this because that way, there's no confusion that I've never been a big fan of the -1 representation for inverse functions, but I guess we're kind of stuck with it. But not in this case, though, because we can use the arc. But I would never, in a handwritten test, I would never be, concerned with what a student was doing. Either way is fine. Because I would understand what you meant. Now, the domain into this arcsine function would be between -1 and 1, because if you think about it, the domain here is actually the same as the range of the original function. So no matter what you put in there for sine, you're not going to get -1 to 1 is the only possible range of values. So that now becomes the domain right here in this notation where sine of y equals x. And then so they could have picked lots of different segments to do this, but they picked this one, -pi/2 to pi/2. That means when you put in something between -1 and 1, you're going to get this range of values. So they're kind of using, you see over here where quadrant 4 and quadrant 1, they're using negative. But where you have to be careful on this, though, is numerically, you can't treat, the whole idea of coterminal angles, in a trig circle. You'd be used to this angle I have right here. You'd be used to that saying, 7pi/4 right there. But 7pi/4 is not the correct result if you're applying the inverse trig function to it, specifically arcsine. It would have to be treated as -pi/4. Even though they're coterminal, their values are specific. So you see what I put in here now, I use degree mode to make it a little easier. And calculators, radians, it's not going to show you pi. Maybe the calculators will do that one day, or maybe some do now, and I just don't know. But of course, somebody listens to this video, 10 years from now, you can probably laugh about it. But anyway, at this point in time in 2017 here, I just do degree mode so you can see easier instead of just whatever the decimal answer is here. So sine inverse square root of 2 over 2 gives me negative 45. So it's giving me negative 45 degrees, which then has a radian value of negative pi over 4. And these functions have to be 1 to 1 to 1. Like, for example, you might think, well, if sine of pi over 6 equals 1/2, and therefore I'm saying arc sine of 1/2 was pi over 6. So I put this in here to show you, like, well, sine of pi over 6, pi over 6, excuse me, also equals 1/2. Wouldn't arc sine of 1/2 equal 5 pi over 6? No, that's the whole idea of 1-to-1 functions and inverses. They can only have one result there. 1x per y, 1y per x. So, and you see that pi over 6 is in quadrant 1, and it satisfies this range of values between negative pi over 2 and pi over 2. So that's the reason why this can't have multiple answers. I mean, for example, if you were solving a trig equation in a trig class where it says sine of x equals 1/2, you would have two solutions. That's where you'd have to know that you couldn't just trust the calculator only with doing the inverse sine. But I don't want to go into a big long trig video lecture right now, but inverse wise, anyway, going back to that trig equation, yeah, it would have two answers, pi over 6 and 5 pi over 6. But arc sine of 1/2 is only pi over 6, or also 30 degrees. Now here's cosine. I'm not doing all 6 functions here. We're just going to do arc sine, arc cosine, and arc tangent. The same domain, -1 and 1, because that's the output. When you put in something to cosine, you're going to get somewhere between -1 and 1. But we have a new range. So here it's quadrant 1 and quadrant 2. It's 0 to pi. But notice that the similarity between this one and the last one is not what quadrants they're in. Is notice that one value of the quadrant is negative and positive. So you used to have one negative and one positive. Same thing here. So this one's a little bit easier because you don't have to worry about the whole idea of like negative pi over 4 and stuff like that. You're going to get angles strictly between 0 and pi. So like for this one, I did cosine inverse of negative square root of 2 over 2, and it produced 135 degrees, which I'm labeling in blue right here. It's right there at 3 pi over 4. Okay, so there's a graph of it. See, so once again, you have to take a chunk, but it's already predefined. We don't have to come up with this. But see, that green thick bar means that is 1 to 1. It doesn't overlap it twice horizontally. Arctan has the same range as, well, not quite the same range as sine, because it doesn't have equals at the pi over 2. So it goes negative pi over 2 to positive 2. But look at the domains, kind of interesting. It goes anywhere from negative infinity to infinity. That means for a tan inverse, you can put anything in there. Like, for example, I put tan inverse of 50,000, and I have it in degree mode here, 89.999, so you can see it's close to 90, and tan inverse of negative 50,000 is close to negative 90. Well, let me just tell you real quickly why this works that way. It's not that critical, but these limits will be good to know for other things that are done in Cal 2, especially. These are good to know. But the reason for that is because, you know, a tangent sine over cosine, so they're undefined at pi over 2. But the idea of the arctan says that, okay, as you get closer and closer to 0, sine is getting closer and closer to 1, which that's not a very big number, but the key here is that the cosine is close to 0. It's a very, very small number. So even if you take a number that's maybe close to 1, like 0.9999, and you divide it by something that's 0.0000000 whatever 1, that makes it a gigantic number. So that's why it's getting closer to positive infinity and negative infinity. So the limits, the one-sided limits here go to either infinity or negative infinity, but this is the interesting part down here in red. Yeah, because the sine, cosine, stuff like that, going to infinity doesn't tell you anything because it's oscillating all the time. But this is good information here. I put one of them in Maple. I didn't do both. So the limit as x goes to infinity of arctan of x might not seem like it makes any sense, but it does, based on what I was just explaining. it would be pi over 2. And then negative infinity would produce negative pi over 2. All right. Here's another idea here, and we're going to use variables for this because obviously this could be done straight in the calculator, and where's the fun in that, right? Because you really wouldn't have to use the technique I'm about to show you here, but we will when there's variables in there. So what we're doing here is we're gonna have something, it might be like cos of arcsine of 2x is what we're going to be doing here shortly. But this is a number 5 over 13. So what we're going to do is we have to build a triangle to come up with this. So what we want to do is we want to let theta represent everything inside the parentheses. So over here, theta equals arcsine of 5 over 13. By the property of inverse functions then, that means sine of theta would just be 5 over 13. Essentially, sine cancels out arcsine if you applied sine to both sides. You're not multiplying by sine, you're applying sine to it. Sine of arcsine. So sine of theta equals 5 over 13. Well, I think I could draw a right triangle that has sine of 5 over 13. Got a right triangle. I'll put my theta here. Opposites 5. Hypotenuse is 13. And of course, if you have a right triangle and you know any two sides, we have a famous theorem called the Pythagorean theorem that will allow us to solve for the other side. And that will give me 12. So once your triangle is built, you can then go back and look at what your outside function was. In this case, it was cosine. So now cos of arcsine of 5 over 13 just becomes cosine of theta. Well, cosine of theta then will just be the adjacent 12 divided by 13. So it's 12 over 13. And as you can see, I did this in the calculator and did fraction, and it produced 12 over 13. All right, so now we're going to do these algebraically. We want sine of arc cotangent of 3x as an algebraic expression of x, means it's going to be something with variables in it there at the end. And so as I did before, I'm letting theta equals arc cotangent of 3 over x. So that means cotangent of theta equals 3x. But when you do a trig function, they're always rational, aren't they? Like, in other words, opposite over hypotenuse, adjacent over hypotenuse. Well, 3x is not a fraction. Well, here's a nice little math trick that you can take 3x and make it a fraction by putting it over 1. How about that? Hey, now it's a fraction. Surprise. So cotangent is, tangent is opposite over adjacent, so cotangent would be adjacent over opposite. So 3x goes down here, 1 goes here, and then Pythagorean theorem. Now, I see people miss these on tests sometimes because a very common mistake here, hopefully you won't make this mistake, is they don't square the 3. So they'll square this and they'll say it's 1 plus 3x squared. No, it's 9x squared because you squared the 3. And then that means the hypotenuse then will be the square root. I don't know why I reversed the order here. There's no logic behind why I switched them. It's not wrong, but if you were wondering, why do you do that? I don't know. But it's perfectly fine. So be careful to square that 3, and then look at what Stewie says over here. Please don't ever do this. This really hurts Stewie's feelings here. That's some really, really, really bad algebra. See over here with the 3 and the 9, that's just a brain fart. That's just a minor brain fart. You didn't square the 3, you put 9. That's really takes some serious effort to screw that up. You cannot take square roots of added and subtracted terms individually. Multiplied, yes. Like, for example, the square root of a times b is the square root of a times the square root of b. But not when they're added and subtracted, so be careful not to do that. So now you see I've got my triangle built. So now I can look and see what was my outside trig function. It was sine. So basically it means I'm finding sine of theta. So I go look at my triangle. Sine is opposite. Hypotenuse is the radical. There you go. 1 over the square root of 9x squared plus 1. I don't care about rationalizing denominators, but if you're picking the right answer on a test or quiz or something, you might have to multiply top and bottom by the square root of that denominator. So, yeah. But personally, I don't care. All right, so there's how we do that technique. Now this is take a look at this. I don't know. I might have taken that off my quizzes. I've had some quizzes before. It's not a big deal, but this could be good, useful information for you in other classes you take. Science, engineering, things where you're evaluating inverse trig functions. Is that, all right, for example, let's look at secant and cosine. Secant is the reciprocal of cosine. The secant function is 1 over cosine. That's true. That's always true. It's still true. But the inverse trig functions do not work that way. In other words, arcsecant is not, I repeat, not 1 over arc cosine. It is not. The reciprocal comes into play for the argument of the function right here. That's where you take the reciprocal, not 1 over the entire thing. So arc cosecant of x equals arc sine of 1 over x. And arc secant of x equals arc cosine of 1 over x. And then arc cotangent of x equals arc tan of 1 over x. So actually, to evaluate arc secant of number 2, you would have to take arc cosine of 1 over 2. And once again, maybe I don't know if the calculators are ever going to expand. Because the reason why I'm doing this is because they don't have all, they have all the trig functions. Well, no, they don't either. They only have, you still have to use reciprocals. But they only have 3 of the inverse trig functions on the calculator. Yeah, they only have 3 right there in blue: sine inverse, cosine inverse, tan inverse. So that's probably just more useful information. Right over here, in other words, if this algebraic expression is correct, now of course you have to be careful what numbers you put in there. It's not going to work for all real numbers. So I picked something close to 0. And this is not important. You're never going to have to actually do this for any reason. But what I did is that means I took that 0.1 and I put, I evaluated sine of arc cotangent of 3 times 0.1, and it should equal to that radical expression if you put 0.1 in there. Now, of course, to do arc cotangent, what I showed you right here, arc cotangent of 0.3, I have to do arc tan, inverse tan of 1 over 0.3. So it's sine of inverse tan of 1 over 0.3. Look at that number. And then I just took that answer we got right here, put in 0.1. Look at that number. Like I said, there are some numbers this wouldn't work for, but the fact that it does match here, it's probably not a fluke if you're using 0.1. So that probably means I did it correctly. All right, well, here's another one. Tan arc sec of 4x. So I let theta equals arc sec 4x. That means sec theta equals 4x over 1. And 4x, but then like I did the last problem, you got to put it over 1 here. So secant's hypotenuse over adjacent. So you have to use Pythagorean theorem to get the other side. That's going to be the square root of 16x squared minus 1. So once you have your triangle built, let's see. Then we can get whatever our outside trig function is. So here it's tangent. So this becomes now tangent of theta because we defined theta. So tan of theta will be opposite over adjacent. So obviously I just didn't put divide by 1 because I didn't have to. So it's the square root of 16x squared minus 1. All right, derivatives of trig functions. I provide these for you. I can't remember if it's on a formula sheet, or I might have just put the formula next to whatever the problem was on the test. So if you don't have a formula sheet for it, that means it will be in the problem itself. If not, there'll be a sheet that has these listed. Because obviously, if you only had to do 1 or 2 of these on a test, you only really need the ones that you have to use. So I've got a proof of one of these down there on the very last page. I'll show you. So I'm not going to read all these out since you can kind of look at these. Like I said, I don't make people memorize them, but one thing I do tell people is if you were taking a class where you did have to memorize them, notice that, so we have sine, tan, sec. If you put the word co in front of all these, co makes cosine, co-tan makes cotangent, co-sec makes cosecant. So I'm not saying these relate to each other, mathematically, other than the phrase co. But anyway, notice that the difference between the right side and the left side, if it says co, it has the negative in the numerator where it doesn't on the other side. Otherwise, they're the same. So I guess if you don't ever have to memorize these, don't worry about it. But it's a neat trick if you ever did have to. So there's the right side's just the negative of the left side. So I think, I'm probably not going to get overly complicated here, but I think obviously derivatives are easier than antiderivatives. Although I may get a little, fun little chain rule in there to see how, like this next example, to make it a little bit challenging. But I don't want these to get too rude or nasty. But this is a perfectly good one right here. F of t equals arcsine of t squared. So the derivative would be, so t squared is u, of course. So basically it's t squared prime, the derivative of t squared, over the square root of 1 minus t squared squared. So that the derivative of t squared becomes 2t, so it's 2t divided by the square root of 1 minus t to the fourth. All right, so you got to be careful here. I brought back something we've seen before, the general power rule. You can do that, or you can use kind of a chain rule thing. I mean, I think this, if you go through this carefully, it's not too bad. Just got to be extra careful here. I wrote it out like if you let w equal this inside, then y equals w to the fifth. So you can sort of do a like dy dt chain rule would equal dy dw times dw dt kind of thing. All right, so anyway, but here's how we're going to handle this. We're going to treat this as if it was like u to the, another way we can take just like u to the fifth, not w to the fifth. Same thing. I don't know why I didn't use u. Maybe I didn't want to confuse it with the formula right there. But bring down the 5, the outside, like right here. Leave the inside alone for now. Don't take the derivative yet. So it's like 5w to the fourth. So it was w to the fifth. So it's 5w to the fourth. So you just bring the 5 down, leave that alone in the middle, drop the exponent down to 4, then take the derivative of what's in here. So then we'll now use this arc cosine formula to take the derivative of what's in there, which is t cubed. So it's negative u prime. So it's negative the derivative of t cubed. So it's negative 3t squared. And I didn't write it out here, but the t to the 6 comes from t cubed squared. So t cubed squared would be t to the 6. So that looks perfectly good right there. If you were picking a multiple choice answer, the only thing I might see they might would do is bring that negative 3 up front and just call the whole thing out here, negative 15. I mean, you don't have to do that mathematically. I'm just speculating of what an answer choice would look like. All right, so oh yeah, I kind of just wrote the chain rule. Don't worry about that. Once the problem's over, don't worry about this. I just put that there if you want to see it. That's not a big deal. Arc sec 2x, we got a formula right there. So go ahead, we want to use the absolute value because if it's in the given formula, be sure to use it. So it's arc sec of 2x, so it's u prime, which will be 2 on top, over the absolute value of 2x. And then that does reduce. Look what I wrote over here. The absolute value of AB is the absolute value of A times the absolute value of B. So that absolute value of 2 would come out and be 2, and they cancel, but it would still leave the absolute value of x there. How about this one? Arctan of square root of x, which that's x to the 1/2, of course. So u prime, x to the 1/2, you take the derivative, it will be 1/2 x to the negative 1/2 over the bottom, which will be 1 plus x to the 1/2 squared. So that's just x, so it's 1 plus x on bottom. I put a flag here indicating like if this was a, handwritten question on a test, that means that answer is perfect. If you're trying to get a multiple choice answer, you might need to do one more thing here. It's just the appearance at this point. So it's taking the x to the negative 1/2 and dropping it back down and making it the square root of x. And then that 2 right there in the numerator comes down with it. I don't think the answer would be like distributed. I would be shocked if it was distributed. But I think it might look like that, where it leaves that 2 square root of x factored out on bottom. All right, let's take a look at this one. All right, this one's got a product rule going on here, so we can refresh our memory of the product rule real quick here. So the derivative of x would be 1, so that's why there's nothing there, times arctan of 2x, plus x times the derivative of arctan, which I have it right there. So the derivative of 2x would be 2 over 1 plus 2x squared. So I left that alone a minute. And over here, natural log, which I do not believe at this point in time we've actually learned the derivative of natural log yet. My notes, as I'm making this video, this section has moved from Cal 2 to Cal 1, but we have not got to the natural log. So I guess we can forget about that right now. I have it written over here, and you'll see this later. Yeah, when I had these notes in Cal 2, obviously that had been covered, so my apologies there. So I think we can go ahead and stop there, or I guess I could finish anyway, and just in case. But this is the formula for the derivative natural log of this u right here. It's not hard by any means. That's the good news. But yeah, you're not responsible for this if this is in Cal 1. If it ever moves back to Cal 2 somewhere down the road, then this video, then you would be responsible for it. So 1/4, and the derivative of 1 plus 4x squared is 8x. And then we have 1 plus 4x squared on the bottom, which is the u. You wouldn't probably have to simplify this, but I just kind of did this to show you that these two terms actually canceled it, and it simplifies to arctan of 2x. But here's something that we will learn. I know for sure this isn't Cal 2. It won't move. So right now we're learning the derivatives, but in Cal 2 we'll learn how to integrate this thing. So you see the answer simplified to arctan, because remember when you take a derivative of something and you integrate that answer, it goes back to the original function. And look what happens if you integrate arctan. It does give you this arctan of 2x. It gives you exactly what we started with right here. So, all right, here's another one. I don't see be doing anything this messy to you for exam purposes, maybe on a quiz, but let's just see if we're comfortable using these inverse trig formulas, and we're good. Derivative formulas. So the derivative arc sine right here, so that's x over 5 is just 1/5 x. So the derivative of x over 5 would be 1 over 5. And then 1 over the square root of 1 minus x over 5 squared. Over the other side here, we have a product rule. So I guess this is good practice for us, the product rule. But I'm not, like I said, not interested for testing purposes to do all this to you at one time. But, like see this part on the right, like on the final, could be by itself or something. Yeah. So derivative of x is 1. And so then you have 25 minus x squared to the 1/2 plus x. Bring the 1/2 down, makes it negative 1/2, then you take the derivative of the inside, which is negative 2x. Well, technically, this is the answer where I have the flag, but I already kind of knew this one was going to simplify. I'm not going to worry about going through that. I mean, if you look at it and have any questions and want to contact me, I'd be happy to help you. But since I know I'm not making you do this on a test, I'm not going to worry about explaining it. But I knew it. But anyway, once again, I was just trying to show you how this simplified answer is integral of that does produce our original problem. Which, once again, that's another thing, a skill that we'll learn in Cal 2 to be able to get from that integral back to this. But you don't have to worry about that. So we have this one, arctan of x over 2. So the derivative of arctan will be the derivative of x over 2, which is 1/2, over 1 plus x over 2 squared. So see, I left that That looks like I did another simplification there, but don't worry about that. And over here, now you can do quotient rule, but since we don't have a variable in the numerator, I mean, if you did quotient rule, that's okay. Don't bring the 2 up. You just bring the x squared plus 4 up and call it -1. And heck, I just did basically a general power rule here, aka chain rule. But so I brought the -1 down. With that -1/2 would make +1/2. Lower the exponent by 1 to make -2. And then the derivative of the inside is 2x. And just for grands, I cancel the 2. That answer's perfectly good enough right there. You don't have to go any further. I did it again just to show you another chapter 8 integral. Well, I'm sorry, chapter 8, okay, that's might not be using the same, we won't be using the same textbook at the time I make this video, so you could, I'll tell you what I'll do here. Well, I don't have a stylus here, but I guess I can, I'm just using a mouse, so I couldn't really write that very clearly, but I can probably do this and call it Cal2 integral instead of talking about a certain section or anything like that. Yeah, that would be make much more sense. And all right, so there we go. Do I have that up here too? No, I just said it verbally. So Cal2 integral, there we go. It's a little more generic. Not book dependent that way. And the last thing I have here is, like I said, just for fun, I don't make you do this, but I'll just pick any one of them. I'm not using the u, I'm just using in general terms of x, but obviously the chain rule makes this numerator u prime. So, but obviously if u is x, u prime would be 1. So I'm proving this using, and you have to use implicit, there might be other ways to do it, I shouldn't say have to. I'm using implicit differentiation. So I'm letting y equals arc cosine of x, which then means cosine of y equals x. Or more specifically, x over 1, because I am going to need I'm going to need a triangle to finish this problem. So if cosine is x over 1, it's adjacent over hypotenuse. And then Pythagorean theorem will give you the square root of 1 minus x squared on that other side. So I could have done the triangle later, but so now I come down here and here's the calculus part. Here's the derivative part. So I'm going to take cosine of y equals x and do d dx as if I was doing implicit. And remember, implicit means, we've seen that already, obviously, right? When you take the derivative, you have to stick a y prime or dy dx, whatever you prefer. I'll just use y prime anytime you take the derivative of a y term. So cosine of y will be negative sine of y prime. The derivative of the right side is 1. So I'm solving for y prime. So I divide both sides by the negative sine of y. So I have -1 over sine of y, which is the same as negative cosecant of y. And then I just go back to my triangle to figure out what cosecant is. Since sine is opposite over hypotenuse, that means cosecant is hypotenuse over opposite. So that means it's got the negative there though. So it's 1 over the square root of 1 minus x squared. So if you felt like having some fun and want to try that with any one of the other ones, you certainly could. You're not obliged to do that, but it might be fun. All right, so I believe that's going to conclude this video on inverse trig function differentiation.